Today we're going to learn about our second comparison test called the limit comparison test. Now, if a sub n is greater than 0 and b sub n is greater than 0, that is, if our series given and our series we're comparing it to are both positive, and the limit as n goes to infinity of a sub n over b sub n is equal to some value, L, equal to a number, when L is a finite and positive answer, then we can conclude that the series as in the summation of n equals 1 to infinity of a sub n and the summation as n equals 1 to infinity of b sub n are both convergent or both divergent. So if I pick a convergent series and I find that this statement is true, the limit as a sub n over b sub n is true, then it converges. If I pick a divergent series and I get a answer for the limit, it diverges. So let's look at our first example. Let's figure out what we're going to compare this to. Let's compare this to 1 over the cube root of n squared. So that means that's 1 over n to the 2/3 power, which is a p series. And this p series has p equal to 2/3, which is less than 1. So we know this is a divergent p series. Then I'm going to do the limit as n goes to infinity of a sub n over b sub n. So limit as n goes to infinity of this series I came up with to compare it with, divided by the original given series. Now, since we're dividing a fraction divided by a fraction, we're going to flip that bottom fraction and multiply. And that gives me the limit as n goes to infinity of the cube root of n squared plus 1 divided by the cube root of n squared. Remember our limits rule, I can take that cube root out of the limit and write this as a cube root of the limit as n goes to infinity of n squared plus 1 over n squared. And we can simplify that down by distributing that common denominator to each term. And so I have the limit as n goes to infinity of 1 plus 1 over n squared, and all this is underneath the cube root. And the limit of 1 is 1. The limit of 1 plus 1 divided by n squared is 0. So I have the cube root of 1 plus 0. The cube root of 1 is 1. 1 is a finite positive number. So we have a true statement here, so this test works. So since I was comparing this to a divergent series, I can conclude that this series diverges by the limit comparison test. Okay, let's look at our next example. We're going to determine if the summation of n equals 1 to infinity of 3n squared plus 5n divided by n 2 to the n over n squared plus 1 diverges or converges. And so I need to figure out what to compare this to. So I kind of think of it sort of like the end behavior model. And so I look at this and I figure out what is our highest degree on top and highest degree on bottom to kind of figure out what to deal this with. And so if I distribute that 2 to the n and get rid of the parentheses on the bottom, and then my numerator on top, the highest degree is 3n squared. And my bottom, my highest one is 2 to the n over n squared. And then the n squares cancel out. And so this is 3 over 2 to the n. So let's try comparing it to something similar to that. So an easy one that's similar to that would be just 1 over 2 to the n. So we're going to compare it to that series. Okay, this is a geometric series where r is equal to 1/2. And since 1/2 is less than 1, this is a convergent geometric series. Okay, and so I'm going to find the limit as n goes to infinity of my given series divided by my comparison series. Now notice last time I did my comparison over my given. It doesn't matter which order you write the fraction because it's just going to be a fraction. Just do one series divided by the other series. Okay. And then what we usually do on this, we can just skip that step of dividing by a fraction, because we're going to flip and multiply the second fraction, so I'll just flip and multiply. And notice that simplifies, that 2 to the n cancels out, so I'm left with 3n squared plus 5n over n squared plus 1. And then again, I can use my end behavior model for this rational function and figure out that this limit goes to 3. 3 is a positive limit. It's finite and positive. And so I was comparing it to a convergent series. So my conclusion is this given series converges by the limit comparison test.